Okay, shall we make a start? It's my pleasure to introduce Theo. I'm not going to attempt to say his last name. For those of you that don't know, Theo is a new lecturer who's just joined in psychology, and he's going to be telling us about an overview of his work. He's joined us from York. So over to you, Theo.
Yeah. Hello, everyone. Thanks for coming. I'm Theo Karapanagiotidis. And this, like Chris said, I recently joined the School of Psychology. It's about like a month and a half ago now. And this is my first talk at Sussex. So I was debating if I should tell you more details about one particular study that we're running lately, or maybe if I should give you an overview of multiple studies that I've run over the last few years, kind of like the big picture of my research interest, what they involve. And because this is my first year at Sussex, I decided on the latter. So this is going to be, which means it's going to be a talk with, it's going to have quite a bit of methods in it, and quite a lot of results. Hopefully, it's not going to be too confusing. If it does become too confusing at any point, I apologize. Please feel free to stop me and ask me about any questions that you might have. Also, because this is going to be an overview, I'm not going to go into too many details about each one of the methods. If you're interested in any of these methods or the results, feel free to get in touch at any point and we can discuss about them. So basically, like I said, this is going to be an overview, and in a nutshell, what I'm interested in is how we can use the structure and the function of the human brain in order to better understand our thoughts. And you might ask why we want to do that. Well, not because we want to have control over our thoughts, I promise. Our reasons are more noble. You see, depending on the type of thoughts that you experience, we have lots of evidence that they're showing associations with multiple behavioral outcomes. So depending on the type of thoughts that you might have, for example, there are some good associations. So some particular thought patterns, they can facilitate problem solving, they can refine future goals, they can help you enhance creativity, or they can even ease the feeling of loneliness. At the same time, some different thought patterns, some different kinds of thoughts, they might hamper comprehension during talk. So if you're not really paying attention to what I'm saying right now and you're thinking your own stuff, you won't be able to follow. Or depending on, again, the type of thoughts that you have, especially we have evidence about past-related thoughts. This has been linked to higher levels of unhappiness, and also it can lead to intrusive thinking, repetitive thoughts, as well as depression and anxiety. So basically, we have some good associations, we have some bad associations, and you're old enough to remember spaghetti western from the 60s. We also have, you know, what might be coming. We also have the ugly associations, again, based on the thoughts that you're experiencing. And by ugly, I mean some problems, some issues that we have when we're trying to measure, again, a feeling of your thoughts. For example, we know that thoughts can be different depending on the context. You experience different thoughts when you're resting on your sofa compared to when you're out with friends or when you're going for a walk. Also, there are different for individuals. One of us experiences different thought patterns, and they can be temporarily dynamic, so they change all the time. The first thing that people often say when you're asking them about their thoughts is like, "But my thoughts change all the time." So that's true; they're dynamic. So that's an issue that we kind of have to find a way to solve. Also, your thoughts are private, right? I don't have any way of accessing your thoughts other than asking you about them. So we are relying on self-report. We have to ask you about your thoughts. There is no other way. And this, of course, introduces biases. So subjects are biased to when they have to report about their thoughts, and sometimes they're not even aware of their biases. So they might be unaware. At the same time, every time I stop you to ask you about your thoughts, because that's the only way to get a feeling of your, get an understanding of your thoughts, I stop the cognitive process. That's of course your thoughts. So I stop your thoughts, and that on its own can change your thoughts, the content of your thoughts. and it can potentially contaminate them. So even if you know that I'm going to ask you about my thoughts, you might be feeling different stuff. If I keep interrupting your thoughts to ask you about them, at some point you're only going to be feeling that. You're only going to be feeling something again ask about my thoughts. So this is not going to be your kind of like thought pattern that you would normally have in a situation like this. So, like I said, my interest is to see how we can use structure, function of particular brain regions, whole brain function, dynamic neural function, whole brain hierarchy, kind of like so many, all the weapons that we have available in order to attack this problem and try to solve some of the ugly associations I was telling you about, in order to better understand the good associations. In my opinion, importantly, in order to see if we can solve any issues with the bad associations, especially in the case of mental health patients. So I'm going to give you an example about each one of these, but before I start with any of these, the most important one, how do we explore behavior? So how do we ask you about your thoughts? And like I said, we are relying on self-reports. So it's quite simple how we do this. Really, we call this experience sampling. So we sample your experience. How? By just asking some simple questions. And you can, I don't know, unfortunately, this is not really working, but you can see some of the questions here. We have multiple questions asking you about the content, the particular thought pattern. We're not interested in the details of your thoughts. We're interested about their type. So, for example, some of the questions here that you see, my thoughts were about the future, my thoughts were about the past. These are the questions that we normally ask. And we call each one of these dimensions. So we have multiple questions, so it's kind of like a multiple, we sample your experience across multiple dimensions. And you can see the labels there of each question. So like the vivid dimension is basically essentially a question that says, my thoughts were vivid as if I was there. And so on. And we do this in many settings. So we do this in your daily life. You might get a text that will point you to an online website where you go and answer these questions. We do this in the lab while we're doing a task, which could be a hard task, a boring task. Sometimes, quite often, we use boring tasks. So we help the participants kind of like start thinking about their own stuff rather than really concentrating on the task, which is what we would normally want, but not in this case. And of course, we also do it inside the scanner. So we put people in the scanner. We normally have resting state scans. I mean, there's nothing for the participants to do. They just lie in the scanner. There's a fixation cross. And at the end of the scan, we ask them about the thoughts that they were experiencing during the scan. And once we have that, we have multiple dimensions, like I said, so multiple questions, and we could potentially use them in kind of analysis as independent variables, but there are too many of them. So what we usually want to do, and they're also correlated with each other. So what we want to do is we want to identify principal patterns of variance among these questions. And one of the ways that we do that is by running a principal component analysis. So this will identify, so this will take us in with all the dimensions that we have, and we will identify some principal components, some principal patterns of thought, as we want to call them, as we normally call them, that explain most of the variance in our data, right? And for example, here, this is an example like we had a daily life experiment, and we were asking the question that I showed you to the participants. And then in the end, we run a principal component analysis. It identifies these 4 principal components, and you can see them here. The detail component, we name them quite often. So we have the detail component, the social component, the modality component, and the emotion component, which are the components, the patterns of thought that explain most of the variance in our data. And then the word clouds on the right, I'm going to be using quite a lot of word clouds in my talk. So I want to explain how they work. Basically, they're showing some terms. These are all the individual dimensions. If you remember the labels of each one of these questions. And they're showing the weighting of each dimension in that particular component and the association if it's positive or negative. So the bigger the font size, the bigger the weight of that particular dimension in this component. And if it's a red color, it's a positive association. The blue color is a negative association. So basically, your detailed thought pattern here, the detailed question has a high weight, the evolving question has a high weight, whereas in the episodic social component, the second principal component, you see that the future dimension has a high weight, and the self dimension has a high weight as well. So if I answer that might refer about the future, I would score high on that particular principal component, on that particular thought pattern. Now, what is interesting and what we have found from different studies is that these principal patterns of thought are quite stable. So they stay the same across different conditions. So these are exactly the same principal components from different data sets. So we had another data set coming from behavior, looking at their behavior in the lab. And we also had another one where the participants were being scanned and we run PCA on our data. And these are the components that we got, and as you can see, they're quite similar. So there is a pattern between thoughts that stay the same, which kind of like says that, for example, if there's a tendency of thinking about the future, there's also a tendency to thinking about yourself. That's like the second component. Or some people tend to think in images, some other people tend to think in words. You see the negative association there, and so on. So we have these principal patterns of thought remain stable. What's also really interesting is that they also kind of remain the same within subject. So even though our thoughts are dynamic and they change all the time, and I might be thinking so many different things in like a few minutes, nevertheless, if I have a tendency for my thoughts to be past related, yes, the details might be different, but they were always going to be about the past. So always, not always, but there is a high chance they're going to be about the past, and we have evidence for that. That each one of us kind of like has a pattern of thought, like kind of like the default pattern of thought, if I can use this term, that we kind of like fall back to, especially when we're resting, especially when we're mind wandering and thinking about other stuff. And this is quite stable across contexts, like I said here, and within subject as well. So it's not as dynamic as we thought things were. Now you can imagine that these components, you can imagine them as kind of like defining a lower dimensional space. If you were here for like Peter's talk last week, he talked about this encoding model space. So you could, in the same way, define your experience space, if I may use the term, where basically you have your principal components on each axis. And then depending on the answers on these questions, I can place you somewhere on this space, right? There's subject 1 in the lab, for example, subject 2 in real life, and so on. So I can place your experience in this space, which is something that I really want to use in the near future, because I think that this is going to be quite useful placing people in that space in order to see some of the stations that otherwise might be difficult to find. Like I would imagine, for example, patterns of thought from patients clustering in some particular place of that experience space. And this is the data, these are the data that we use in our general linear models that we run as independent variables. So the principal component data that we have. So let's go to the neuro imaging side of this now. So I'm going to start with structure. So what can structure tell us about individual thought patterns? So a few years ago, in order to get some information about the structure, we ran a diffusion-weighted imaging study. Jamie, a couple of weeks ago, talked about diffusion-weighted imaging. In case you're not familiar with it, it's a different kind of scan. Basically, it will look at the diffusion of water in the brain. It will give you a description of the white matter structure in each participant's brain. And we'll also make these lovely images, which are not significantly, but they look nice. And we ran that. So we had like diffusion-weighted imaging data. And then we ran what's called track-based spatial statistics to be assessed, which essentially it will align the white matter skeleton for each one of the participants. And then you will do your analysis on a voxel by voxel basis, kind of like how you would normally do it in a functional experiment. And we also ran some probabilistic cartography analysis in order to get a sense of how the white matter tracks go along the brain. So diffusion, you get information about white matter structure and white matter cables in a way. It's kind of like the cabling that connects the gray matter regions. And we also had some resting state functional MRI data for these participants as well. And on day 2, we asked them to come to the lab, and we had like experience sampling. We run experience sampling in the lab, which again, they were just like doing the boring task, and then we asked them about their thoughts. And we ran PCA to identify these principal patterns of thought. And now, structure is relatively stable, adult life, and then these findings were on another day. Sorry, this we ran this on another day, so the metrics that we had about the thoughts were on another day. So any kind of association that we had here, they were kind of like show kind of like a trait-related association with the structure of the human brain. And we did indeed find some robust associations between the structure of the human brain and particular thought patterns. So you can see here, for example, we had a temporal limbic white matter region that you see here in red, which showed increased functional anisotropy. This is a metric that we often use in diffusion-weighted imaging analysis. Basically means that there was a difference in the structure of the participants, that they reported thinking more about the future and the past. So they were engaging more in mental time travel. And this was the white matter region that you see here that showed a difference for these participants. Of course, we had that region. We wanted to see a kind of like white matter tracts pass through that region. So we ran our probabilistic tractography analysis, and then we wanted to see if there's like an overlap with any of the known white matter bundles that we have. And there was an overlap with the right fornix, the spinal tract, and the inferior fronto-occipital fasciculus, and you can see the overlap here. So basically, we have white matter region different for mental time travelers, if I may use this term, and we wanted to see what kind of like we saw what kind of like big white matter bundles pass through that white matter region. We also wanted to see where they terminate, most of them, which gray matter region do they terminate. So we ran our analysis and we found that the region that this white matter tracts that pass through our white matter region here, the gray matter region that they terminate is basically the hippocampus. So we have the structural difference of people who engage more in mental time travel that is related to white matter tracts that terminate through the hippocampus. So it was quite an intuitive result, and we're really happy with the result. At the same time, because now we have a gray matter region, we have a hippocampus, that's our region of interest, and we also had some resting state functional data. We ran a simple with going to how we can use the function of a single brain region to understand the kind of thoughts. We also ran a seed-based correlation analysis, like a straightforward analysis. We took the time series of the hippocampus and we correlated that with the rest of the brain to see if there's like any other region that kind of like show increased correlation, functional connectivity, as we call it, with the activity of the hippocampus. And again, we found that the same people who reported engaged more in mental time travel, when they had that structural difference, these same people, the functional connectivity of the hippocampus with the medial prefrontal cortex was increased. So they showed an increased functional connectivity of the hippocampus with the medial prefrontal cortex. The people that reported engaging more in mental time travel. Now the medial prefrontal cortex is the core region of the default mode network, and the default mode network is often right up with increased cognition, with like spontaneous thoughts, mind wandering, and so on. So again, we had a quite intuitive result here, I would say. People showing a structural difference, engaging more in mental time travel, engaging the hippocampus. And this is a case where the hippocampus basically integrates to sharing more information with NPHC, which is basically a core region of their DMN. So what have we learned from these two studies? Basically, that elements of ongoing thought can be partially constrained by the white matter architecture of the brain, and engaging in mental time travel spontaneous episodic thought. So mental time travel obviously relying on episodic memory processes is a case where the hippocampus and the cognitive network kind of like act together. Now, moving to whole brain function, we had a look at the structure, we had a look at the function of a particular region. We also wanted to see what the kind of like the whole brain can tell us about people's thoughts. And for this one, we had, as for another study, we had resting state functional data from a big cohort, and we also had experienced some that we asked them about the thoughts at the end of the standardization in this case. And then, because there are many evidence linking particular thought patterns with physical and mental health, we also asked the participants to come again for a second session and after to answer some questionnaires that kind of like gave us some metrics about dispositional traits, about their physical and mental health. And here, because we're interested in whole brain function, again, we want to find a way to reduce the dimensionality of our data, or instead of using all voxels, we run another dimensional reduction algorithm, which is called the independent component analysis. And in this case, we try to identify ICA, or surely we try to identify independent sources of your data, to identify some components that can maximize the covariates. These sources, when we combine them all together, they give you, what you're getting from the brain. And this is what we run. We run an ICA, and these are the networks that we got from this analysis. Pretty standard networks that you would normally get when you're running an ICA on resting state data. You see like the DMN and other networks as well, like auditory, visual networks, and so on. So now we went from our whole brain space, we kind of like went to a lower dimension, kind of like using only these components as our inputs for our GLM analysis. And we run a standard graph theory analysis that we normally run in this case, which basically is looking at the correlation between these maps that I just showed you. So in pairs, and then you're trying to see if there are any differences between the correlation of these maps that might be related to differences in what the participants reported about their thoughts at the end of the scan. And we did have, again, some robust, distinct associations. So we found that increased functional connectivity between the precuneus and a lateral frontotemporal network for people who was engaged in more visual image. So if you reported the more visual, then there was an increased functional connectivity of the precuneus with the frontotemporal network. Now, the precuneus is another core region of the DMN. DMN is often associated in our, we often find the DMN in our analysis. And then we have a frontotemporal network, which is kind of like includes regions associated with semantic cognition, kind of like multimodal network. So our interpretation of this result was this increased functional connectivity, but it's kind of like supporting the cognitive processes that we write to visual mental imagery. And we also had, if you remember, this measures about dispositional traits, and we had another significant pattern here. So in this case, it was going to the other direction. So we had a decrease in functional connectivity between brainstem and the visual lateral network for people who scored higher in measures of self-consciousness, rumination, and attentional problems. So we kind of like call this kind of like an internal attention state. So here we have decoupling. So these two regions are not sharing so much information when people are engaging more in internal attention. We have the brainstem, which is often associated with ADHD. Also, it's a brain region that has been associated with heart rate variability, and also is a kind of like a regulator of autonomic function to the brain, as well as global connectivity. So we have this important region not sharing so much information with the visual lateral network, sensory network, which could be the kind of like process that underlies underlies when someone is going into an internal attention state. So you kind of like stop paying attention to the environment, you kind of like get lost in your own thoughts. This could be why, because there is a decrease in shared information across sensory networks and brainstem, which is like an important region for all the reasons that I just mentioned. Now, importantly, we also had a moderation effect. So one of these relationships was actually stronger when we took into account the other one as well. So we have brain function, we have thoughts, and then we also have dispositional traits, physical and mental health. We know there are relationships between physical and mental health, in particular thought patterns. We know there are relationships between neural data and dispositional traits, as well as neural data and ongoing thoughts. Now here we also see that there's like a more complicated relationship between the moderation effect. I'm not going to go into it, it could be a little bit confusing. So basically, the correlation between the frontal temporal and precuneus and the visual imagery was higher for people who also scored higher in this brainstem visual cortex association. The detail of this moderation effect is not so important in this case to follow in the sense. What is important, in my opinion, is that accounting for all these three measures can actually be helpful and can actually help you identify variants that are hyperactivity and explain. So basically what we've learned from the study, unique neural patterns reflect trait variants, both when ongoing thoughts at rest and associated with dispositional traits. And accounting for trait-like dispositional patterns is important because, like I said, it could help you better understand brain-thought relationships or vice versa. If you're interested in brain physical mental health relationships, asking about someone's thought that actually help them understand these relationships better. And asking about someone's thoughts literally takes this question takes an average probability to answer them. So like whatever scan you're running in the scan, you add another name to this question. That can be really useful and else definitely when you get. Moving to dynamics now, right? So all these analyses so far, they have been based on the time average. So all these GLMs, we're looking at the time average neural activity over the period of like 9 minutes or 7 minutes, depending on the resting state scan. Now, obviously, the brain is dynamic; it has like changes its function all the time. So we want to see is looking at the dynamics of the neural data, neural function can help us better understand someone's thoughts. And when you're looking at dynamics in neural data, you're limited by the temporal resolution, of course, of your data. And if you're using EEG or magnetic spectroscopy, then the temporal resolution already, so the dynamic resolution is going to be awesome. You might be able to see changes like a millisecond scale. But when you're using fMRI, then obviously you're limited by how often you acquire a new brain picture, like your TR, which in our case was 3 seconds. 3 seconds when you're talking about dynamics is still like a long period of time. So I might say the brain does like so many things in like 3 seconds. Nevertheless, if we think that we want to relate that to dynamics of your thoughts, I would say they're about on the same scale. Like your thoughts are dynamic and they change, but they change at the scale of seconds. So looking at how the neural function changes with the scale of seconds, try to relate that with like the dynamics of thoughts, I think we are at the right scale in this particular case. And we used fMRI data, and this is how we kind of like got some metrics about dynamic neural activity in the brain. And in this case, we used hidden Markov models. I'm not going to go into too much detail about them. I'm more happy to later on if you're interested. So basically, the hidden Markov models, you will have your input, which is going to be time series, not from all the muscles of the brain, but like some functional participation or any kind of participation of the whole brain. You get your time series and you input that into the HMM algorithm. Now the algorithm is going to look at the time series all at once, and it's going to try to identify distinct recurring patterns in your data. So it will identify a pattern that is associated with a particular whole-brain activity and a particular whole-brain connectivity that is recurring, and that's going to be, for example, your state 1, and then we'll find a different pattern, a different whole-brain activity pattern, and a different functional connectivity pattern. It's going to be your state 2, and so on. And it will give you transition probability matrices, like it will tell you if you are in state 1, what's the probability of going into state 2, state 2 of going to state 3, and so on. It will also give you time series of the states. So it will say point 1, you were in state 1, and point 2, you were in state 2, and point 3, you were in state 4, and so on. And once you have that, you can calculate a bunch of dynamic metrics. So you can calculate, for example, switching rate. So how often I switch from one state to the other. You can calculate dwell time. So once I visit a particular state, how long it takes me on average to leave it. You can calculate interval length. So once I leave a state, how long it takes me to revisit the state. So you have all these metrics that you can calculate based on dynamic functioning of fMRI data in this case. And it follows the Markov properties of the state that you're going to go, only depends on the state that you were before. So we use the HMMs in order to get an understanding of the dynamics of our neural data. And this is the analysis pipeline for this study. Like, for example, we have session 1, we had, again, resting state scan, 256 participants, another big cohort here. At the end of that scan, we asked about their thoughts. And then again, session 2 in the lab, we also have to answer some questionnaires about people health, because we also want to see the dynamics with these dispositional traits. And then we wanted to reduce the dimensions that we often do. So for the behavioral data, again, we do the PCA. For the thought data, that gave us the principal patterns of thought. And we also run a PCA, separate PCA on the physical and mental health data. For the brain, in this case, we didn't run an PCA before, but we just did functional calculation. And the idea of the mouse space is a functional persuasion that covers the whole brain. That kind of like gave us the time series that we use in our HMM communication. And then, as I said, we run the HMMs, and you can see, for example, this is the activity of state 1, or the main activity when someone is in state 1. This is its functional connectivity when you're in state 1, and then this is the activity of state 3, which is different compared to state 1. That's why the algorithm picked in different states, different functional connectivity matrix, and so on. And from those, from that composition, calculated the dwell time. So once you are on state, how long it takes to leave the state. So like how difficult it is for someone to leave the state once it enters that particular state. And that was our independent variable, and we used that in order to run some multivariate multiple regressions. So basically, the independent variable was the dwell time, and the dependent variable was either the principal patterns of thought or the principal components for the well-being that we see in the position. And these are the states that we got, 7 of them, with different patterns of activity each one. And I'm not showing the functional connectivity here, but here with chord clouds, you can see the cognitive terms associated with these states based on the meta-analysis. So basically, you take this pattern that you have and you find studies that reported similar patterns, and you see what kind of terms, cognitive terms, this study reported, and that's basically what you get here. So, for example, you see that we have a state that kind of like was sensory related, and we had like state 7 is a state where quite a lot of regions of the default mode network are activated, bright colors activating, blue colors that they are deactivated, and as you can see from the cognitive terms, you get terms that we would normally associate with default mode, non-default mode network activity, or like engaging in spontaneous thought, mind wandering. Like, for example, being off task, it's blue, so it's negative association being off task. or like mental states and autobiographical theory. So these are cognitive terms that go and describe our dynamic states, time-varying states. And once we have that, we run through multivariate multiple regressions, and we found some significant associations between the dwell time of state 3 and state 7 with ongoing experience. So the longer you spend on state 3 at each visit, then you reported engaging more in future thoughts and engaging more in problem solving. And state 3, like you see here, is kind of like a task state. So we have like regions that we will often associate with like a particular task, like control regions, attention network regions, and is associated like staying a bit of time on this particular state. Was linked to like reporting, engaging more, kind of like future of the problem solving, solve something that you care about in the future. Also, we had another association with state 7. State 7, like I said before, DMN mostly regions, and the longer you got stuck in this state, and it was difficult to read that state, it was associated with experiencing past-related, negative, intrusive thoughts, kind of like a rumination pattern, like a negative thought pattern. So the longer you spend on that state, again, like showing DMN activity, kind of like being involved in like when you're disengaged.
Yeah, and so we first is going to they're looking at the brains themselves,
there is some, they're not exactly they're not exactly like opposites, but sometimes we might get like this, and like say in the same way as you get like having the DMN being uncorrelated, dorsal attention, you might get like states which they use over like one of
it's so you don't need more than the very small might have somewhere for us to deal with. If you're allowing it more than you're getting, that's something different.
That's a great point. So basically, you are dependent, like any kind of composition network, any kind of like you are really dependent on the number of states on the house. I mean, now we know brain has 7 states, right? So that's already. Yeah, no, I mean, obviously you are dependent on that. And the less states you ask, then you're going to kind of like bring them together. Like the more you ask, then you might start seeing open states, which are basically one of the other. And so on. So you are dependent on that. What we did in this case, and make sure that I'm not very robust, what basically like around the number of states, and we see that we still get obviously if you ask for 100 states, then that we're going to start having trouble assigning different patterns for each one of the states. There is a way to ask that how we can like get rid of the ones that are not so useful by only giving us for 2 minutes. So yeah, there is a problem. This is saying like how many states of origin you can ask for, how many clusters you can ask for, how many states you can ask for.
One question.
Yeah. Yeah, you do. I mean, in the end, you do. There are some ways that can kind of like try to say, well, we do that. So, but in the end, you normally actually have to choose one. Sometimes it's easy. Like for example, with problems like this, you have like a republic task. Then you know you have a hypothesis that I'm going to look for 2 states. I think probably not for the topic. So you ask for 2 states and you will get like this. You will think nicely your data. In this case, there is a certain thing like this when you see. Okay. So these were our these were our results for when it came to ongoing thoughts. And this is state 7, like state 7 here, have the association with like a maladaptive thought pattern, if I may use this term, like a rumination thought pattern, negative, past-related, intrusive thoughts. it also showed similar association with physical and mental health. So the more you stayed in that state, the higher you scored, and that's probably the asked in session 2, give matrix for this one. They scored higher in trait anxiety, trait rumination, social anxiety. So it was nice and like to see the convergence for state 7. So what we have learned, dynamic neural states can describe cognitive states, and states mimicking the brain's response to a task, that was state 3 that I told you, with the dorsal attention when the parietal region being activated, and also states that were more similar to patterns that we normally see at rest, the DMN kind of like pattern that we see at rest, were linked to self-reports of cognition. The one was the biographical future planning, the other one was ruminative thinking, basically, and also as well as associated with dispositional traits, so evidence of neural dynamics linked to like particular thought patterns. Now, finally, for brain hierarchy, what kind of brain hierarchies tell us about our thoughts? And when I'm talking about brain hierarchies, sometimes you might have like what is seemingly a chaotic system, like if you think about it for the brain, and you look at individual neurons, it's a seemingly chaotic system, like here, for example, with the starlings. But if you zoom out a little bit, all of a sudden you might start seeing some patterns emerging, some large-scale hierarchies emerging, which they're not just there, they're also influencing the dynamics of the system and the behavior of the system. So in a similar way, how would this work in the brain? How could it put some constraints on the dynamics of the brain and the behavior and our behavior in a similar way? So how would this work in the brain? Brain organization can be understood as large-scale hierarchies, and large-scale hierarchies, we get them by running again and not the composition method. We can get them by running the PCA or data, ICA data. In this case, we chose to run a diffusion embedding algorithm, which is different from the diffusion weighted imaging data talked about at the beginning. But it kind of like still kind of like tries to track not the flow of water in this case, but kind of like the flow of connectivity in your data, if I might use this term. Diffusion embedding works better in theory with nonlinear data compared to PCA and ICA. So this is what they've used here on brain data from the human phone project data set, so like more than 100 people at the time. And these are the principal components that we're getting from this analysis, which can be thought of, described as kind of like a hierarchy. And here we don't call them principal components, we call them gradients. And the diffusion embedding is going to try to it's going to try to do both PCA and ICA together. So it will try to maximize the variance and also maximize the covariance within each component. So in this case, gradient 1, the principal component 1 from this diffusion embedding is going to give you a whole brain map that explains lots of variance, it explains most of the variance, but at the same time, it will also show you the regions that correlate more to each other. Like anything in red, there are regions at one end of the gradient, one of the component that have like talk more to each other, and anything else that is in blue, they're like on the other end of the gradient, which are talk more to each other. Kind of like I said, combination of PCA and ICA. As you can see, gradient 1 or the principal component 1 is basically separating the brain into multiple sensory regions on one end, and then kind of like more DMN, higher order cognition related regions on their other end. Then the second gradient explains the second best variance in this case, kind of like separates the whole brain into sensory, motor, and visual regions. And then the third one is kind of like separates the brain into like regions that we normally see in the task environment, the task setting. And on the other end, you have regions that you will normally see them in resting state scans. And once you have these 3 dimensions, these 3 gradients, then in the same way, again, you can go into some kind of like brain space. So they can define your axis, and then once you're in that brain space, you can have your states or whatever map and see where it falls on that in that brain space. And this is where our dynamic states fall in this brain space. And what was interesting about this is that you see that these states do not fall randomly anywhere in space. You see that there is a pattern, and they tend to kind of like all be situated at the outer edges of that brain space. So you see like the contour plots show you a new distribution, and you see that the states that we got from the dynamics, they kind of like tend to fall to occupy particular spots in this brain space that describes all brain hierarchies basically. And if you remember, state 3 had an association with thoughts, and then also state 7 had an association with thoughts. And then as you can see here, gradient 3, the third kind of like hierarchy, kind of like these two states fall at the outer, at each end of like this hierarchy. The task end, then with state 3, then on the rest end, state 7. Now, what we have learned from here, neural hierarchies, because from what it looks like, the dynamics are not random in that right space. So we can say that neural hierarchies can provide coordinate space describing dynamic patterns, kind of like constraining where these dynamic states are going to go in that space. And again, same neural hierarchy that kind of like separates task and rest can also be discriminative of patterns that we see, patterns of thought that we see, like in that case, in this particular case, future probability or intrusive related. Now, to finish next steps, what I'm interested in at the moment, basically we have some evidence from a study that we ran where we saw that the dorsolateral prefrontal cortex is associated both with off-task thinking, so thought patterns when you're not engaging in a task, and also associated with on-task thinking. So it was involved in both cases, and it kind of like can be thought of, this is evidence that you can think of the DLPFC as kind of like a regulator, kind of like suppressing, kind of like keeping a balance between on-task thoughts and off-task thoughts, depending on the context, because sometimes it could be beneficial actually to not be thinking about the task. If there is no task or if the task is boring, it could be beneficial to have like thoughts unrelated to the task, which, like I said at the beginning, can enhance your creativity, for example, or can engage yourself in problem solving. But some other times it can be really detrimental, right? If you really need to focus on a particular task and you keep thinking about, when you're going to go and meet your friends, then obviously you're not going to perform your task so well, so that will be detrimental. It looks like from this study that the DLPFC plays an important role in keeping that balance depending on the context. Kind of like, it looks like it's a regulator in this sense. And you see where it falls on the brain, the left DLPFC, by the way, not the right, which is interesting, something to look for. That's our finding here. And you see where it falls, and this is where it falls overlaid on state 7 that we found before. And state 7 was the one that was associated with that intrusive, negative ruminative thinking. So you see it here with white borders, basically. And you see that it's negative in that state. So it's not activated in that particular state. So the longer you get stuck on a state where VMN regions are high and DLPFC activity is really low, the more you report experiencing negative thoughts, intrusive thoughts, and so on. And if the DLPFC regulator might mean that the tendency to ruminate could be associated with lower recruitment of DLPFC. That's something that we really want to look at, like in the near future. Left DLPFC is also associated with, like, there is. We want to hopefully be able to run some TMS study as well here, kind of like sub DLPFC, and see if we can change its activity and see what kind of effect this will have on people's thought patterns or their mood, especially in the case of patients. For example, they have been administering TMS, repetitive TMS, left DLPFC for drug-resistant depression. So it is an approved kind of like method to relieve patients of their symptoms. It works for some, it doesn't work for some others, and they don't really know why. We think that this might be related to that. So we think that actually the types of thoughts that people experience might tell us something about why, but it's the case why it doesn't work for some others. And the summary, Yes, structural properties of the brain can constrain its function and influence our thoughts. Neural interactions linked with sort of memory processes and visual imagery. They are recruited for generating thought content. The whole brain dynamics addressed are linked to ongoing experience as well as psychological well-being. And for future directions, like I said, we can do all these things. We can deal with the agony association that I told you at the beginning. So imagine a situation where we train an algorithm to identify particular thought patterns that are linked with particular neural patterns. Once we train this algorithm, then I can give it new data. In theory, obviously, in practice, it's not going to be that easy, but in theory, I can give it new data, and it might be able to identify your thought patterns without me having to stop and ask you about it, so without basically interrupting the process. A mind reader, essentially, right? So we're not there yet, far away, but in theory, it could happen. And also, this would be extremely useful in cases of like with patients, like even like patients like being in a comatose state. You can use something like that to see maybe they can like or like patterns of psychosis that we have, or in mental health patients for assisted diagnosis, diagnostic tools and optimizing available treatments. And with that, I would like to thank you all very much, and also thank people that are involved in this. Oh, well.
No, it's great. I was wondering if your aims at the end of identifying brain states. What is that like? You go with EEG or maybe?
No, it really isn't that, and you would get a bit there by having great resolution. So your species, one of the ones that would be at scale of milliseconds. So there, you can start talking about different frequency, right? So with frequency, signal drops, which is really useful under like averaging from like a more average rate. Okay, that would be it's actually, I would dare to say that would be probably even better for this kind of thing, better than how the easy or energy get like files like 7 volumes, how many times they don't compare. Yeah, and then you can either do this on the sensor, like or if you're PG, you can do the PG as well, especially with the source. The frequency balance, how I can
Yes, you can put it back to so most of the day was done on people that are not really I just wondering how you sort of factor in something by
it should, so basically with these kind of things you can concatenate all the data and you ask for like kind of like a group states that kind of like describe your average participant. Once you do that, then you can identify those parts that they kind of like fall, like falling asleep or like playing notes, because they're going to be further away from the group in a sense. So you might have like some state, it might come out in the end like a state which is kind of like a dozen of like the falling asleep state, which you might have like some participants visiting that state more often compared to others. And you can tell what state this is based on what's active on that state, what's functional activity of that state between different brain regions. So you will have a way to basically the algorithm might get a sense of it and kind of like identify a separate neural state. Ideally, you wouldn't want to go. I mean, like you would want your this like around the same, like alertness, whatever. So in this case, the other thing you can do is you can either put everyone together and see their differences on those group states, or you can train the algorithm on, like the typical those, and then force those states to data coming from ADHD patients. So then you might see significant differences on like what kind of states they visit patients compared to like controlled ones, which could highlight like particular difference in their brain function.
So I would then imagine that you can change that. The other steps that you mentioned, but
Yeah, absolutely, and I think training someone will affect their default states or default brain functioning, and it will also affect their default thought pattern. So I have like, this is a thing that I'm like exploring at the moment. So I believe that we kind of like, whenever there is nothing of interest to us, we can like fall back to our default thought patterns, the ones that kind of like stay the same across time within individuals. So we have a tendency to imagine visuals, like images, whenever there is nothing like what that is of interest, we tend to go back to that. When we have a tendency to think about the past and ruminate, we go back to that. So we can push someone out of that zone. They will go back because the priors are strong and they're going to pull them back. But do it enough times, again and again, repeatedly, you might actually be able to change their brain functioning that supports this kind of like process, and at the same time change their thought patterns to a new default and like get them out of that maladaptive state. Yes. That's how we got rather important is you get like helping those stuff like fitness we also were also proposing to actually follow exactly the same things like the application. It's also going to be like that where we can longer term short term. Yeah, so say also, I think the senior in the next one is that's no, in this case, no, and yeah, I'm not sure, but like there is a tendency to always be there, especially like but that's kind of showing like so it's not so clear why this might be this prioritization going on. Yeah, absolutely, yeah. I mean, in this case, yeah, I'm remember there was I don't remember if there was like some question that we do. Yeah, but yeah, it's okay. Yeah, we can talk about it in the office. Thank you very much. Thank you.
Next year.
Yeah, thanks, man.
You mentioned beginning with the traits.
No, we didn't have